Okay, I've been talking about measurement, I've been talking about observations, been talking about data, been talking about a variety of things, and the rubber needs to hit the road. We need to clearly talk about some of these issues related to data collection and so on. So this is a brief lecture on measurement and related issue called scales or measurement scales and implications of those for statistics. By definition, measurement is the use of a rule to assign a number to a specific observation of a variable. This is how we collect data. This is how we get data. We make measurements. And measurement is nothing special. It's just the use of a rule to assign a number to a specific observation. Your rule can be lay down the tape measure and start at the beginning and look at what measure it's closest to, or it could be put something on a scale, or it could be count, or it could be whatever. It's not a difficult or complicated concept. Now, there are some problems with measurement rules, or some issues with measurement rules that we need to talk about, or measurements, and that is validity, reliability, and properties. Validity is how well measurement rule actually measures the variable that we're interested in. Reliability is how consistently the rule assigns the same number to the same observations. And the last issue is the properties. Now, validity and reliability are critically important. You're going to talk about validity and reliability a lot in research methods, and I'm not going to talk about it much more after this. So you can sort of put those aside, but I am going to talk about properties. We're going to start with a category property. Observations assigned the same number are in the same category, and observations assigned different numbers are in different categories. When numbers have this property, we say that they have the category property. Numbers can also have something we call the ordinal property, and that is when they can be used to order or rank the observations from those that have the least of the variable being measured to those that have the most. So if we can order the observations from least to most, from biggest to smallest, from greatest to smallest, then we say that those numbers or those measurements have the ordinal property. The equal intervals property is whenever two observations are assigned numbers that differ by exactly 1 unit, there is always an equal interval or difference between the observations and the actual variable being measured. That means that if we have a number assigned to an observation that's 2, and we have a number that's assigned to an observation that's 4, we assume that the measurement 4 has exactly twice the amount of stuff we're measuring than the value of 2. Now, this becomes a problem when you're measuring something like depression or anxiety. And if somebody has a depression score of 10 and another person has a depression score of 5, the question becomes, does the person with the score of 10 have twice the depression as the person with 5? That's an important question to consider. Measurements can or don't have to have equal intervals properties. We'll talk about what that means a little bit. And the last property that numbers can have is they can have an absolute zero property, or measurements. A value of 0 is assigned as a measurement only when there is nothing at all of the variable that is being measured. Okay, so what does this mean? Well, if we take these 4 properties, we wind up with 4 measurement scales: a nominal scale, an ordinal scale, an interval scale, and a ratio scale. And nominal scale has just the category property, and ordinal scale has both category and ordinal properties. In an interval scale, the numbers have category, ordinal, and equal intervals properties, and in a ratio scale of measurements, they have all 4 properties. So let's talk about a few of these and go through some examples. In a nominal scale, numbers have only the category property. For example, area codes. Area code 262 represents numbers in South Central Wisconsin and not South Central LA. It has a category property, but it has no other properties. For example, 262 does not have more of something than area code 215. There are no ordinal properties to zip codes or area codes. Zip code is another example of a nominal scale. Area code 524 is not twice the area code 262. There are no equal intervals when we're talking about numbers and area codes. And area code 000, if it existed, does not mean the absence of an area code. There are no absolute 0. Another example of a nominal scale is baseball uniform numbers. How do these numbers meet the criteria for a nominal scale? Well, we can categorize number 12 is different than number 13, but number 12 isn't smaller than number 13 necessarily, or number 12 isn't half of number 24. 12 merely means Aaron Rodgers. 53 means Clay Matthews. It doesn't. Football and baseball uniform numbers are in a nominal scale, and all they do is they name somebody, and that's where nominal comes from, is name. There's some other examples you can come up with. Think about that a little bit. All right, the next scale we need to talk about is the ordinal scale, and these are when numbers have both the category and ordinal property. So, or to finish in a race, like Olympic medals, for example, on the ordinal scale. First place is different than second place. You get a gold, you get a silver medal. They have the category property. First place is better than second. Second place is better than third. They have the ordinal property. You can order them. In the 100-meter dash, the difference in time between the first and second, though, is not necessarily the same as the difference in time between the second and third place finishers. So places in a race or Olympic medals do not have the equal intervals property. And zero place means, well, I don't know what it means. Although first place in gymnastics could mean that you've made zero mistakes, but the absolute zero thing here is, I don't even know how to interpret that. So we think of order of finish as an ordinal scale. Class rank, how does that qualify as an ordinal scale? Well, if your class rank is second and your friend's class rank is 10th, that doesn't mean that you're 5 times smarter than he is, or 1/5 as smart, or whatever. There's no relationship there. You could have very close GPAs, and the difference between 2 and 10 is not the same as the difference between 10 and, let's say, 18, I guess. Interval scale is when numbers have the ordinal, category, ordinal, and equal intervals property. So an example of that is temperature measured in Fahrenheit or centigrade. Measurements of the same temperature represent the same amount of heat. So if something is 33 degrees and something else is 33 degrees, we say that they're the same temperature. They can be categorized. 33 degrees is higher than 32. But importantly, in this type of scale, of 1 degree change in temperature always corresponds to a specific amount of heat. So for example, the difference between 32 and 33 is the same as the difference between 33 and 34. 0 degrees, however, does not mean the absence of heat. It's not absolute zero. In Fahrenheit and centigrade, 0 is as cold as those guys could get. Actually, 0 centigrade is the freezing temperature of water. That doesn't mean there's the absence of heat. Heat being the molecular motion. Women's dress sizes appear to be measured on an interval scale. How so? Well, a size 4 is smaller than a size 6, a size 2. So size 4 dresses are like size, so they have the category property, they have the ordinal property, they probably have something like an equal intervals property. However, 0 doesn't mean the absence of a dress. In fact, actually, when I learned this, so for you men out there, this is sort of crazy, it blew my mind for a minute, and that is there is actually something called a 0 size dress. It's a very small dress, but it's not the absence of a dress. The last scale is the ratio scale, and these are numbers with category, ordinal, equal intervals, and absolute zero properties. Reaction times measured in seconds, weights, heights, lengths are all on the ratio scale. Measurements of the same reaction time represent the same amount of time. That's a category property. Higher reaction times mean more time to react. That's the ordinal property. And 1 second change in reaction times represents the same amount of time. And 0 seconds represents instantaneous reaction, or no time is required to react. I don't know if that's possible, but these do have the absolute 0 property. Measuring Kelvin represents a ratio scale because 0, Kelvin is a little bit different than centigrade, and that is absolute 0 is absolute 0. So what? Why am I taking this time in the book, why am I taking this time in lecture to describe these different measurement scales? Well, first of all, it prevents you from making unsupportable or confusing statements. For example, if Sharon's class rank is 1 and yours is 3, you wouldn't say that you're as third as smart as Sharon. Okay? When numbers are used to represent things, we have to understand what properties are those numbers representing. Descriptive statistics, those that describe statistics that describe a sample or describe a set of data, depend in part on the measurement scale. It makes very little sense to add or average area codes. You wouldn't add area code 608 and 314 to equal area code 922, and you certainly wouldn't average those. You wouldn't say the average area code of 608 and 314 is 461. That doesn't make any sense. That's nonsense. That's because area codes only have they're a nominal scale. They only have the category property, and we can't perform mathematical functions on category level measurements. Inferential statistics, as we're going to learn, also depend in part on the measurement scale. We're going to be asking this question for the remainder of the semester. What type of measurement scale are we looking at? All right, well, that's it for this lecture. Talk to you soon.